Okay, so we're going to look here at our redundancy when we're doing our Gaussian elimination, and that is the second of our two special circumstances. The other one was inconsistency that we've just looked at. So what we're going to do here is we want to consider the following set of equations. So we've got x plus 2y plus 2z equals 11, x minus y plus 3z equals 8. I'm going to have 4x minus y plus 11z equals 35. So what I'm going to do is, I'm going to put it into my augmented matrix, take my coefficients. I've got 1, 2, 2, 11, 1, minus 1, 3, 8, 4, minus 1, 11, and 35. Okay, dotted line, augment it, brackets. There we go. So when we're looking to do this, I'm going to cheat here, reduces just to give us 1, 2, 2, 11, 0, minus 3, 1, minus 3, and then 0, 0, 0, 0. Okay, so you can have a look with that one. That is the thing that you're going to try and reduce into upper triangular form, and you find that we kind of have done that. So if we've got it here, we can still see my zeros in that bottom corner, and then I've got stuff populating the rest of it. Only what I've got here is I've just got an entire row of zeros, and unlike the last video, if I've got nothing on this side, it makes absolute sense to have nothing on the other side. And so the row of zeros here, purple, tells us the equation are redundant. So what does that mean? Well, that actually just means there are no unique solutions. Okay, so this is what creates a problem. So in the first instance we looked at, there was one answer. There was one value for x, y, and z that made these things work, and that was it. Okay, in the last one we looked at inconsistency. There were no values for x, y, and z that met those conditions. And here, what it means is that there are in fact quite the opposite, because there are in fact an infinite number of solutions. So what we need to do here is we need to pick one of our variables to keep. Okay, so our answers are subject to something. Okay, now what we need to be able to do at this stage is we need to pick apart how we can tell if it's inconsistent or redundant. Further on down the line we'll start applying these things to actual conditions, but just now we don't need to worry about that too much. So what we're going to do is we're going to take row 2, and row 2 should give me minus 3 lots of y plus z equals minus 3. So I can rearrange that to give me y is equal to z plus 3 over 3. Okay, I can use my top row here, 3, which I'm actually, I guess, wrongly, let's call it row 1, let's be consistent, ironically. X plus 2y plus 2z equals 11. Okay, and what I'm going to do is I'm going to use this version of y. And so whenever we're doing it, our answer is going to be dependent on a variable, but what we want to make sure it is we want to make sure it's the same variable. Okay, so shoving in our numbers, we start to move towards x is equal then to 11 minus 2 lots of z minus 2 lots of y. So the first thing we'll do, let's just get everything over at the other side. That makes x then equal to 27 minus 8z over 3. Okay, so again, I'm just taking this, substituting it in for y. What that tells me then is the general solution is x equals 27 minus 8z over 3. I've got y equals z plus 3 over 3, and z equals, no, just z. Okay, z was whatever z was. Okay, and that is the thing that we've picked to use as our condition. Sometimes we might say, okay, well, let z equal t, some random number. In that case, you would have y equals t plus 3 over 3, and then here x would be 27 minus 8t over 3. But that doesn't really feel like that makes any more sense. You've just said, let this unknown number be a different letter to represent the same unknown number. So that's what we've chosen to do here. A particular solution can be found. Okay, so it's not all doom and gloom. Particular by picking a value for z, of z, for z. For example, we could make z equal 3, and I'm going to make z equal 3 mainly because it divides by 3 in the fractions. So that's going to make it a little bit nicer. If we do that, if z is equal to 3, the solution would be x is equal to 27 minus 8 lots of 3. 8 lots of 3 is 24. 27 minus 24 is 3. 3 divided by 3 is 1. Y is equal to 3 plus 3 is 6. Over 3 is 2. And then z equals 3. Okay, and that would be what we wanted. Theoretically, we could give you any value for x, y, and z, and you could work out a particular solution from that. So we could give you a value for any 3, but again, we can see it's a lot easier if I just tell you z, because that's the thing you're going to put everything else on. That's the variable that all of these things are dependent upon. Okay, so when we've got a row of all zeros, it becomes redundant. Okay, that equation essentially tells us, well, it tells us literally nothing. Okay, it is of no use to us. And what we are trying to do is we are trying to solve 3 variables with only 2 equations. Okay, and we said right back at the start, in order to find a definite answer, there needs to be 3 equations for 3 variables. Okay, and that is the point in this.